Hi everyone, I'm Yier Lin, and I'm a fourth-year PhD student from Math Department of Columbia University. Today is a great pleasure to talk about a recent project about the Lyapunov exponents of the stochastic heat equation with general initial data. So this is a joint work with Promi Gasal, and our paper is available on arXiv, so feel free to have a look. So what is a stochastic heat equation, or SHE? It's a stochastic PDE given by the following form, with C to be the spacetime white noise. As long as we start from any reasonable initial condition, the solution to the SHE exists and is unique. And if we start from any positive initial data, then the solution will remain to be positive at all times. The SHE has this interesting connection to the KPZ equation introduced by Kadar, Priest, and Zhang. So this connection is given by the half-color transform, which means if we take the logarithm of the stochastic heat equation, then this H will solve the following KPZ equation, which is a very nice model for the random interface growth. So actually, the result of our talk will be two-folded. On one hand, we compute the Lyapunov exponent of the stochastic heat equation, and on the other hand, we use this to derive a large deviation principle of the KPZ equation. Okay. So for the stochastic heat equation, we're interested in two kinds of initial data. The first one corresponds to a narrow wedge solution, where we start our SPDE from a direct mass at time at 0. And the other initial condition corresponds to, we set it to be exponential of fx, where f is some measurable function from R to R, which is allowed to be random. The reason here we set the initial data to be exponential of f instead of f itself is due to this connection to the KPZ equation. So in this setting, actually, if you take the logarithm of the ZF, then you will solve the KPZ equation starting with the initial data f. And also this setting guarantees we start from the initial data, which is positive. So actually our solution remains to be positive at all time. So now for the stochastic heat equation, we define something called the Lyapunov exponent. So the piece Lyapunov exponent is defined to be the following limit, if it exists, about the piece moment of the stochastic heat equation. So we use gamma p to denote this Lyapunov exponent, and in particular, we use this gamma narrow wedge, or gamma f here, to denote the Lyapunov exponent of the stochastic heat equation, starting from narrow wedge, or the general type of initial data, this exponential of f, okay? So the Lyapunov exponent of the stochastic heat equation has a strong connection to the large deviation principle of the KPZ equation. And the connection is given by the following. If we can show this limit exists for every p, in other words, like every p's Lyapunov exponent of the stochastic heat equation exists, then you can prove a large deviation principle of the KPZ equation with the rate function defined as to be the Legendre transform of the Lyapunov exponent. And this either really corresponds to the speed of the KPZ equation, like in the sense of Laplace number. Okay. So Dawson and Tsai, they prove for the stochastic heat equation starting from narrow wedge initial condition, the Lyapunov exponent is given by this pq minus p over 24 for all p greater than 0. So actually their proof relies on a very careful analysis on the exact formula for the stochastic heat equation starting from narrow wedge initial condition obtained by Amir Cohen and Costel. Okay? So we want to compute the Lyapunov exponent of stochastic heat equation starting from a general class of functional valued initial data. And in general, there is no such nice formula. So actually in this talk, we'll explain how to get the Lyapunov exponent without relying on the exact formulas. So we need to impose some conditions on our initial data. The first one corresponds to when you look at this integration for our f. So we want this limit exists for every p, okay? And for every p greater than 0, and actually this limit will define a function g. Okay? So I need to admit that in our paper, actually, this condition is formulated in some more complicated version, but this is mainly due to the technical aspect appear in the proof. And this simple formulation is the main spirit behind it. So I just formulate as this here. And the other condition corresponds to some regularity for the initial condition. So we ask the upper tail for the increment to be super exponential. So for example, you can take f to be Brownian motion. And actually, this condition does not force our f to be continuous, because you can see for any bounded measurable like initial data f, it will satisfy this inequality. Okay. So as long as like our f satisfies the aforementioned conditions, then the stochastic heat equation starting from this exponential of f, we can compute its Lyapunov exponent to be this pq minus p over 24 plus the g function, which is defined as this limit for every p greater than 0. Okay, and as a result, under some mild condition on g, we can obtain an upper tail large deviation principle for the KPZ equation starting from f, with the rate function to be the Legendre transform of the Lyapunov exponent. So here we have this p cube instead of pq minus p. It's because we have moved this t over 24 to the left-hand side here. Okay. So actually, like our theorem applies to a wide class of general functional value initial data. So let me just mention one important example where we consider this f to be a two-sided Brownian motion with the deterministic drift on both sides, and the a to be their maximum. Then we can compute the Lyapunov exponent to be this narrow wedge part plus plus this g function part. Okay. And if you look at the large deviation, you compute the Legendre transform, something interesting happen. First, like our rate function depends on whether like a is greater than 0 or not. And in particular, when a is smaller or equal to 0, the rate function has a crossover happen at s equal to a squared over 2. Okay. So this is basically about our result. Now let's talk something about the proof heuristic. So how do we compute the piece Lyapunov exponent without using the exact formula? So actually, the starting point is a lemma from Cohen and Hammond, which allows us to express this stochastic heat equation starting from exponential of f in terms of the narrow wedge solution times this initial data. And they're coupled in an independent way. Then if you want to compute the piece moment of the left-hand side, it suffices to compute the piece moment of this integral. And heuristically, you should expect we can put this p inside this integration. It should not make a big difference as we are looking at the asymptotic of the moment. Okay. But actually, I need to mention, like this step, it takes a lot of effort to justify for our proof. But let's just assume this is true for the heuristic. Then actually you can use the Fubini and the independence between the narrow wedge solution with the initial data so you can first put this expectation inside the integral, then split it apart. Okay, so you have the right-hand side. The second crucial observation is for any fixed time level, the stochastic heat equation starting from narrow wedge is stationary after we multiply by this exponential to the power x squared over 2t. So this allows us to like express this piece moment in terms of the piece moment of the piece moment at time t and 0 times the Gaussian density. Okay, so we can do this replacement and take out this piece moment because it's no longer x dependent, and we can write this piece moment of the f in terms of a product of the narrow wedge solution, and an integral only depend on the initial data. Okay. So we're interested in the Lyapunov exponent, so we want to take the logarithm, divide by t, and let t goes to infinity. Then this logarithm really becomes the summation of two parts. For the first part, actually, it corresponds to the Lyapunov exponent of the stochastic heat equation starting from narrow wedge. And the limit is just pq minus p over 24 as computed by Das and Tsai. For the second part, it only depends on our initial condition, so we really want it to converge. So this becomes our condition imposed on the initial data. Okay. So something more about the proof ingredients. So this is actually the last slide of our talk. So actually, like in the proof heuristics, we have mentioned 3 things. We start from the convolution formula actually obtained by Cohen and Hammond. Then we need to use some stationarity of the narrow wedge stochastic heat equation, as well as this Lyapunov exponent computed by Das and Tsai. So to make our proof rigorous, to make this heuristic work, we really need to verify we can put this piece power inside this integral. Okay. So to do that, we need the regularity condition of f that was also imposed before, and also some other tool which relates to the incremental bound of the narrow wedge stochastic heat equation, which is obtained by Cohen, Gosal, and Hum. Okay. So this is basically everything for my talk. Thank you very much for your attention. Just want to mention I have another recorded talk at the stochastic analysis session about the SPD limits of the higher spin vertex model. Feel free to go and check it out. Thanks again.